Testing, 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 testing. Okay. So I have I don't know who's here already, so hang on. Maybe I should just check. Okay. Sorry, who's Jordan? Oh, okay, sorry. Yeah. Huh? Suddenly, hey, I got Jordan, man. Okay. I got this question that's being asked, and this is not an easy question. This one here. Uh, might take a while for me to settle this one. I'm just wondering whether or not it's worth it for me to go through it now. Um, maybe I should. Maybe I should just do a quick one. Uh, this one here is work management. Oh, hello people. What's going on? Okay. So this one here is from the spec paper. Oof, this one I'm okay. Sorry. I have like I say again. I don't know who's asking this, but it's MCQ, so I'm going through MCQ. But wow, geez. Okay. If you take a mass, right? If you take a mass and then you lift it up. Let's say I lift up this mass. Okay. I bring up this mass a certain distance, right? So let's say a certain distance at this, and then I apply a force upwards, right? So I move this mass up. So my work done, right? Basically, my work done will be equal to force times distance, right? So that will be the my work done. Um, Now the force minimally must be the same as the weight of this box. So it's got to be the weight of this box, which is like mg now, right? Mg. But that's not me by me. This is the weight of the box. But minimally, I need to be able to support the weight of this thing and then move it upwards. The idea here is that if I do that, I don't help it gain KE. There's only gain in GPE. So so my work done is minimally the GPE of this box. So this is equals to mg times d, right? Mg times d, which is basically mgh, right? Yeah. But this particular question is that the mass is hanging on a spring, okay? Hanging on a spring. So I draw a spring for you. So I have a spring and it's attached to the mass, right? Attached to this mass, right? So I draw the mass again like that. I draw a small mass like that. But at the same time, so the difference between the situation now and this situation is that right now Okay, in this situation, I have to apply the full force straight away. I need to apply the full mg straight away. Okay, and I need to be able to lift this thing up, right, immediately. As in, like, by myself. Sorry, not immediately, by myself. So I need to push it up. But for this one here, the spring is helping me, right? So the spring is helping me, because it says that the mass is hanging freely from the end of the spring, right? A student raises the mass vertically. So technically speaking, at the start, right? In fact, at the start, what is the force that the student is exerting, right, on the mass? Actually, right now, the force that he needs to exert is like zero. So there is a tension in the spring, right? There's a spring force, right? And it happens to be equal to the weight because it's hanging freely, right? The question says hanging freely. So it's hanging freely here. Oh, hello guys. Why is there so many people now? Okay. So there you go. So this is like mg, like that. Okay. So in fact, the force that this student is like, exerting is zero at this time. Okay. So what's gonna happen is this, right? He still wants to lift it up. So imagine like I'm in class and then I have my slinky, I attach something and then I'm using my hand to push upwards, right? So there's like a force by the student, right? But at this time it's zero, right? So the F that he's exerting is zero right now, right? Right now it's zero. Um, as it starts to move upwards though, as the mass starts to move upwards, so I'll just draw this on the side here like this, right? As the mass starts to move upwards, the spring gets less, less stretched, right? So the spring gets less stretched. Okay, so you can see the coils like, like condensing, and then the student is exerting more force, right? So the student is exerting more force, right? Kind of like the force that he's exerting, right, is like the difference between the tension and the weight, right? So the amount of force he's exerting, right, the force he's exerting is getting more and more and more, right? Yeah. So it's like it's increasingly increasing. It's increasing, right? The force as he moves upwards, the same distance, right? As he moves upwards, the same distance, the amount of force that he's exerting is, increasing as long as as long as he keeps raising it up and the spring gets less spring force, right? Less spring force, right? So in a way, the difference between this person here and let's say another person there, okay, right? The difference between this person and that person, this person has to exert the full force straight away. This person does less, all right? So the amount of like work that he needs to do is actually less. In fact, if you were to plot the amount of, like, the force and distance graph for this guy, right? If you plot the force and distance graph for this guy, the force he exerts actually increases like that. It's like this, yeah. It's not the full force anyway. The end point is the mg, right? At the point, right, at the point it says raises the mass until the tension becomes zero. That's basically when his force matches the weight of the block, and the tension in the spring is like, the spring is now so slack. We're not compressing a spring. We're not compressing it, so the tension is zero, right? So it's like my slinky. You push it up all the way until the slinky, like, kind of like there's no more like force by it. So the work done by this guy is actually less, right? The work done by this guy is actually less. So the work done by this man is actually less. But for this guy, the work done by him is actually more, because for this guy, if you draw the graph, is a straight graph like this from force, right, all the way to that distance or whatever that distance is, and then the entire area there. So it's like the work done by him. So for this guy, the spring is helping him, right, in that sense. Okay, so um but for the masses, right, for both cases, what is the GPE gained by this guy? What's the GPE gained by this guy? It's actually the same. Both masses gains the same amount of GPE, right? Because they were both moved by the same amount of distance, right? They were both moved by the same amount of distance, right? I move this one by this distance, I move this one by that distance. They have the same weight. MGD is the same, right? Yeah, so they have the same GPE. Okay, but then you have to check, so the gain in GPE of the mass is equals to, right, work done on the mass by the student plus the EPE lost by the spring. So that's the case, right? And that's the whole idea. The EPE that the spring has lost as it becomes less and less stretched is the work done by the student, right? Which is less than the full work done on this side here, the triangle here. Okay. Yeah. So you add up, right? In a way, right? If I were to plot the tension on the same graph here, right? The tension on the same graph here, the tension will be like this, right? The tension graph, right? Let's say I put tension graph like this. And then the EPE lost by the spring will be this area here. So kind of like this triangle plus that triangle equals to the entire, rectangle here, right? The entire GPE here. So yeah, there you go, right? That's why B's answer. There's another version of this question is when you lower it down. Now, the one I've done in class before, right? When you lower it down, I ask you what's the GPE lost by the mass and what's the work done by the person to lower the mass. I think I did it in one of the revisions for C1 SHM, right? Because I was going through a spring question. I think couple of months back, right? I was doing that. So this is like the reverse of that, right? Yeah. Because when I saw the question, I was like, oh man, yeah. I mean, it's the other way around, right? The scenario is the other way around, right? This time around, like, I'm trying to lift it up. So yeah, that's the reason why the answer is B. But if you don't understand it, I'm really sorry. I will explain this again after the prelims, right? But for now, we just have to understand that that's the way to understand this concept here, this question here. It's not easy to understand this one. This one is hard, right? The specimen paper, right? The specimen paper always sets like the standard, right? Yeah. Okay. Um. Now I have no idea who's online. I'm not looking at who's online. So I see MCQ. I'm just gonna go through the MCQs. I'll go through some of these as well, but I know the SLs don't need this, right? But I kind of like have to clear this by today, right? So I do actually have some questions at the back here, but I'm almost done, I think. Oh my gosh, I think I'm almost done. Am I? Oh gosh. I hope so. Hmm. Oh boy. Okay. I've got about like maybe 10 more questions. Yeah, okay. Um, right. Well, I have no choice, right? I was kind of like tied up with family stuff on yesterday. But I guess family's family. I have to deal with it. Uh, Hang on. Oh gosh, I don't even know where am I now. Okay, so I think I'm here, right? Why is it B? So this one here I've explained. So this is Sunday, 24th August, the 9:30 p.m. consult, right? Okay, so this was eh? Oh, okay, yeah, sorry. Then this one here, okay, this one, wow, okay, this is a tough question, right? So this is yeah, it's MCQ, right? So this is a tough one. Does anybody know where this question came from? I'm sorry. Did anybody send this out? I mean, whatever. If you're typing anything to me, I actually can't see anything. So yeah, there you go. Right. So we got 12 people. So let me just do a quick check. Okay. Does anyone know? Does anyone know if Kaja is okay? She hasn't replied me. I hope she's doing better. Does anyone know if Kaja is okay? Okay. I don't. Okay. Okay. Thank you. That's fine. I just wanted to know if she's okay. They didn't reply me, so I don't know whether she's planning to try to split the exams and all that. I was suggesting that she should because if it's a medical emergency, probably might need to. Okay. Does anyone know where this paper come from? Sorry. This is a this is a tough one because this is acceleration versus distance. Okay, all right. If it's acceleration versus time, it's quite easy. The area under the graph would have been velocity. Then you can very easily just find, yeah. But this one's asking for the mass, and they ask you what's the total work done, right? The total work done on the object. sometimes my brain gets stuck. So if you can help me out here, if anybody knows if I'm stuck, right, just let me know. Otherwise, we have to try to figure out the does the area make any sense? Like is does the area have any significance to it? Like acceleration times distance. What's that? Not too sure what that is. Okay. Um, I don't know. Mm, we'll see. I'm a bit stuck here. Work done is okay. No, I got unstuck. So work done, right? So it's force equals work done is force times distance, right? Force is basically mass times acceleration times distance. So acceleration times distance, right? There you go. So acceleration times distance, right? Um, if the acceleration is constant, you just take the constant acceleration multiplied by the distance, and then you can get, your acceleration times distance. But now they give me a graph, right? Acceleration is not really constant, right? But you know what? That means I can find the area here then, right? If I find this area, I multiply it to this one here. Right? I mean, I use it as the A times D there, and I multiply it to 3 kg, I'll get the answer, right? That'll be it. On its own, on its own, acceleration times distance, I don't think there's any significance. Like, there's no quantity where we can say that, oh, acceleration times distance is this amount, this thing. Acceleration times time gives you velocity. Yes, we know that. But acceleration times distance has nothing. So this kind of question, again, is an IB kind of type of question, is that they want you to understand that you can take the area, you must be able to recognize, right? Oh, okay, acceleration times distance, you take the area, right? You multiply it as this, A times D, and then multiply to the mass of the object is given here. That was the work done. That's it. Yeah. So this question here, also done. Okay. Now, whoever's asking it, if you're not here, right? I'm sorry to say that, I mean, I'm explaining it as I'm going through here, lah, right? So I'll just try to reply without typing too much because that's kind of like a lot of effort. Okay. Sorry. And then I'll just screenshot this one. So the area, right? The area here is, yeah, the area here is this one here. So whoever's like online. We have a resistor P is removed, suggest any calculations and the effect on the resistance of Q. Okay. All right. So they show you like, three resistors R, P, and Q, right? Then they ask you like, um, resistor P is removed, suggest without any calculations, what's the effect on the resistance, right, of Q, right? Resistance of Q. So, okay, to be honest, it's a paper two question, but I'm just gonna go through this because this one can be easily done quite quickly, right? Right. But there's an underlying concept behind this, right? And I guess that you gotta know the underlying concept, right? Because I guess that's the important thing, right? Okay. So you've got three resistors, PQR oddly arranged, but Q first, then P and R are parallel. And then they ask you, I remove P, suggest the effect on Q. Okay. Now, of course, the first instinct is I know this from secondary school, right? Like no kick. I know this, right? If you remove P, nothing happens to the resistance of Q. Okay? Unfortunately, that wouldn't be the case for IB, right? Like in secondary school, you probably think your resistors are all ideal. Okay? So in IB, you got to always watch out for Ohm's law, right? You got to so the underlying concept here is Ohm's law, you know? Ohm's law. Okay? So it's like, oh, there's this kind of like this thing, like underlying thing with Ohm's law, you got to anticipate that it could be like it could change, right? You got to understand that Q might be non-ohmic. Now, how am I supposed to know, right? Of course, your first instinct will be denial, right? Or maybe rejection. Will be like, no, why how am I supposed to know that it's something to do with Ohm's law? Or what? Like, the question never even suggests that the resistors are not ideal, right? They wouldn't ask, right? Legit, they wouldn't ask. They wouldn't give you a 2 mark question. I'm sorry to say, but they wouldn't give you a 2 mark question if the answer was that Q was gonna be of the same resistance. All right. So you have to really be a little bit like higher level than this. Okay. Again, I do not know who this is. I legit have no idea. I don't even recognize the handwriting. Right. So you have to really like kind of like be 1, 2 steps a bit more aware. So it is likely, if you're gonna ask me this question, it is likely that you're trying to insinuate that Q is non-ohmic. And if it's non-ohmic, you got to remember how non-ohmic resistors behave, right? So you got to recall that graph, right? So this is a non-ohmic resistor, okay? Non-ohmic resistor. This should be how it looks like, the IV graph, okay? It should look like this. So if you're like, oh shoot, I forgot everything about Ohm's law, B5 video, it's all there, all right? Don't expect me to explain it now because I'm trying to hit as many points as I can, right? If I spend the rest of like what the next 15-20 minutes explaining what Ohm's law is, right? Please don't expect me to be able to like explain it to you in the next 5 minutes. There's no way, okay? You gotta understand that this is a non-ohmic normal resistor type of graph. If it's a thermistor, the graph will go upwards. If it's a diode, it'll go another way. If it's an ohmic resistor, then it'll be a straight line. So some of you might be like, isn't this a filament lamp? Why is this the graph for the resistor? Okay, so I mentioned in my class that a filament lamp is just a normal conductor. A resistor is just a normal conductor. And what normal conductors do is, when it gets hot, the resistance is high. Okay, right? When it gets hot. So as more current flows through, the resistance will increase. The resistance will increase, right? Okay. So as more current flows through, right? So you might want to indicate that here, right? For a graph like this, for a non-ohmic graph like this is high resistance, right? At this point, high resistance. Okay, right? Some of you might be like, oh, is it the gradient? Is it the tangent of the gradient? Absolutely not. Okay, it's just the ratio, right? Ratio. Please go and review this video. There's no way for me to cover all the points, right? I guarantee you, there's no way. Absolutely no way. Okay, so this at this point here is low resistance because this is a normal conductor, right? More current flows through, it gets hotter, the resistance is higher. It's because of the lattice vibrations, right? More lattice vibrations. Okay, long story short, right? The idea is this, and it's a bit surprising as well. If you remove P, okay, what will happen to the overall resistance of the entire thing? You know, yeah. So this is one of those like IB loves to do this. They love absolutely love to do this. All right. So don't get caught, right? Because they are always trying to catch us on students like preconceived assumptions, right? Preconceived assumptions. You'll be like, oh, if you remove a resistor, then the resistance should drop what? Right? I remove resistor, right? Okay, but here's the thing, all right? The trick to this particular question is if you remove P, the total resistance increases. You'll be like, what? So I always suggest to you that if you want to make sure that you want to get the correct answer, you want your marks, right? You double check, okay? Just assume some numbers, dudes. Like 2 ohm, 2 ohm, 2 ohm. Right now, what's the total resistance? 3 ohms. Because you combine this 1 ohm, total resistance is 2 plus 1, 3 ohms, right? But if you go and remove one of them, you get rid of one of them. What's the total resistance now? 4 ohms. Like, whoa, what? Right? You remove one resistor, it becomes 4 ohms, right? Do not assume that it's gonna be the same if let's say you put a variable resistor and you adjust it or something like that. It's different, right? It's a totally different thing. Okay? Go and put in some numbers, right? And go and do the calculations in your head, right? Write it out and you realize, oh, it's like that. So it turns out that the total resistance is larger. If you can see the corrections here, total resistance is larger. And since it's a larger total resistance, it actually will cause the current to be lesser, right? Yeah, because now increased resistance, higher resistance, less current, right? I decreases, right? I decreases. Then you have to go back to this graph and then see, oh, just now the current was this high, now it's this low. It's low current now. Low current means the resistor is colder, not so hot. Colder means lower resistance. So, right, Q will have a lower resistance, smaller resistance, lower resistance. Okay, but this question is about Ohm's law, right? Yeah, that's the thing. You gotta be able to watch out for it. Think about this, dude. They're not gonna give this. I know this is IB, right? But don't treat them like idiots. Okay, all right? They are not idiots. IB has a moral obligation of making it difficult for students to do physics, right? We don't want to have engineers that would design planes that will fall out of the sky, right? So these 2 marks here, double check, question. Why did you give me 2 marks for something so silly, right? Okay, sorry. Next one. Oh, hold on. I think I better reply this one. This one here. And then I screenshot this. Oh, sorry, my mug will be inside. Paste it in. Bam. Okay, good. Okay, this one I done. Right, I'm done with this. All right. If you watch today's lessons, I made some revelations about my. I think it's also me. I think I did teach it, but it just didn't hit me until this morning. Then I realized that events and objects are different things. Okay, but anyway, this got nothing to do with that. Okay, this one here. This is a very interesting question. This is A5. So for the SL students, right? This one's not applicable for you. What's the relationship between L and theta, right? Angular displacement. Now, technically speaking, it's delta theta, right? Delta theta here. Yeah. So I'm okay. What I do know is that L, right? So if L divided by R, right? L divided by R, that's the number of revolutions, right? That the disk will have to roll over. No, sorry. I'm so sorry. 2 pi R. L divided by the circumference. So the circumference of this ball, of this disk, right? Circumference, right? Equals to 2 pi r. Okay. Now I understand. So L divided by 2 pi r is equals to the number of turns. Number of turns. Okay, number of turns. But then I need to relate it to delta theta. So what's the total angle covered, right? So the total angle covered, total theta displaced, right? Total theta displaced, it will be the number of turns times 2 pi radians. There we go. So it'll be L over 2 pi r times 2 pi equals to L over r. Yeah. You see, it's not obvious to me also, you know. It's like I had to like write it out and then I made a mistake as well, right? Cause I forgot that the circumference is 2 pi r. So L divided by 2 pi r is number of turns, right? As it turns, they go down. So anyway, that's the answer for this one. Right, let me just screenshot this one for whoever it is. Seriously, I have no idea who it is. Which probably, is the reason why I can openly flame whoever it is that's posting. Okay lah, I roast you a bit lah, right? I roast you a bit, right? But shoots, yeah, dang it. Yeah, so anyway, there we go. Okay, so couple more. I need to really clear all of this. Does anybody have more MCQ questions? If you have, could you do me a favor? Could you just start sending it in the Q&A room now so that I kind of like can gauge, right? But otherwise you're here for the show, then we'll just do this. Oh man, you're not gonna like this one. Yeah, I remember doing this and I don't like it. You're not gonna like this one, okay? So gonna have to go through this one now. Ugh, that is distaste. That's disgusting. Ain't gonna like it. Okay, all right, we'll just power through this. Okay, haha. So we have a car engine has a constant driving force, right? Okay, at this point, right, I always like to do a little bit of deep dive. I just want you to remember this. A car, right, and its driving force, right? What is the real force for a car's driving force, right? Believe it or not, it's actually friction. So for some of you who have already followed me, like in the earlier days, right? When a car drives off, right? I mean, we love to write it like that. Ah, driving force, driving force. But what is it about this force? Like, what like can the car's engine really make it go forward like that? No, you can't. So the car's true driving force, okay, the real driving force is the car's ability to turn the wheels. Okay. So if the engine is connected to the wheels, which it is, right? As the engine runs, it turns the wheels dig into the ground, and the wheels experience a frictional force from the ground. This is the car's driving force. Okay? But anyway, I digress. Right? So I'm just trying to show you that, friction is a driving force. It's like, what? Some people will be like, what? But to the O-level students, actually you might have done it in O-level TYS before, right? Yeah, a car's driving force is actually friction. Okay. Sorry. Oh man, long day. Okay, friction and air resistance are negligible. So I'm just going to draw a box for the car. There's a driving force here like this. They ask you what's the power versus the time, right? So what's power got to do with driving force, right? What's power got to do with driving force? So P equals to FV, right? P equals FV, okay? P equals FV, right? They tell you that the driving force is constant. So yeah, I'm gonna think that it's constant, right? Yeah, I'm just gonna take it as constant, right? So this term here is constant, right? But the power of the car, if you're wondering where did this equation come from, right? It's in work energy power A3, right? So power is force times velocity. So then you have to ask yourself, what's happening to the velocity of the car? Is it constant, right? If the velocity is constant, then by all means, like B would have been an answer, right? But I suspect V is not constant. Why is it not constant? Because they did say, right, the effects of friction and air resistance are negligible, right? So that means that the car is accelerating, right? Because if there's no force opposing this force, then this is the resultant force of the car. So F equals ma, right? F equals ma, and that means if F is constant, right? If this force is constant, then the a is also constant, right? That's also constant. That means constant acceleration, which also means that if you were to plot it as v against t, v against t, you would expect the velocity to increase linearly with time. So if you have a constant force and you have a variable that increases linearly with time, you kind of like you take on that attribute, and therefore the power should increase linearly with time. So A should be the answer, I think. Yeah, it should be. Okay. So um, V, I mean V proportional to T, right? Therefore P proportional to T. Yeah. I remember doing this and I hated it. So well. Gotta be quick on your feet. Okay, I've got more incoming questions coming in, right? So it's fine. Let me just sorry. Oh boy. Let me just sorry, reply on this thing first, right? So we have this one here, and then we delete this one here. Okay. So climate change, right? B5 again. Right, so let's go to the next one here. There we go. So this particular question It's a bit funny. They want you to talk about the average albedo. So albedo is the amount that's reflected, right? Refraction that is reflected, fraction that's reflected, which basically means this, and this, right? Because you kind of like have to add on the albedo of the atmosphere, the clouds, and the Earth all together, right? So that makes it 30%. So that's 0.3. I think the answer should be A. Hmm. Am I doing this wrong? No, right? Okay. I think that should be the case. Okay, there we go. So whoever that is asking for this one, right? There we go. That is it one. Let's kind of like scroll through. Okay, this is astrophysics. This is E5. They ask you constant radius, Alpha Centauri. Explain how this equilibrium is maintained. So this is talking about, I believe, the hydrostatic equilibrium. That's where the radiation pressure matches the gravitational pressure inwards, right? Radiation pressure outwards and the gravitational pressure inwards, okay? But it's 3 marks, so kind of like makes me feel that they probably want a bit more details. But I believe that this is also part of like the old syllabus. I think the new syllabus is a very watered down version. You don't have to go through too much detail. You can say that Alpha Centauri A has fusion radiation, right? Radiation that comes from the fusion processes. It's a main sequence star, right? And therefore the radiation is project or radiated outwards, right? But the mass of Alpha Centauri A causes a very big gravitational force that um you know that points inwards, right? The equilibrium is maintained when the height when the outwards radiation pressure matches the gravitational forces inwards. And then you can just say that, right? For 3 marks. I believe that should be the case. This one here, oh gosh. Oh dear gosh. What was this? So this one here is asking you to calculate the radius of Alpha Centauri A. Radius of Alpha Centauri A. So luminosity. So I believe you're supposed to compare the luminosity of the sun with its temperature. Yeah. Because luminosity is L equals to sigma AT to the power 4. So you also need the temperature. Uh, I believe you're supposed to calculate the radius based on the radius, the solar radius. Like you have to write R naught as part of your answer. Like I don't think you can have actually a full answer. Does the data booklet have the radius of the sun? Did they provide that? If it doesn't provide that, then you probably will have to just show it as a ratio of the sun's size. I don't think you can get an actual value for this. Yeah, I'm sorry. I have no idea which this is what November 16 paper 3. Okay, you know what? Let me just double check that. November 16. November 16. November 16 paper 3 and the mark scheme. I believe I have to look for Centauri. Centauri. Oh, yeah. Yeah, so this is question 21. So let's look at question 21. I hope I didn't make a mistake on this. Oh, damn. Okay. No, you're supposed to have the 21B part 2. 21B part 2. 21B part 2. The luminosity it is, then they calculate the radius. Oh, am I missing something? Do we actually have the radius of the sun? in the data booklet? Okay, but hang on. How does it help us calculate the radius? Sorry, what? They solve using area. Yeah. Ah, yeah, that's so dumb. Okay, sorry. What? I thought it's something to do with the ratio. Sorry. Yeah, okay. Sorry about that. So luminosity equals to sigma a t to the power 4, right? Is that what you're saying, Dylan? Yeah. Okay, okay. That's so dumb of me. Sorry. So, oh, I thought this was the sun. Okay, so Alpha Centauri A is 1.5 times the luminosity of the sun. So you're supposed to take this and multiply into this, right? So 1.5 times this value to give you the luminosity. Then the area is just 4 pi r squared. Sorry, yeah, 4 pi r squared, right? For Centauri A, and then the temperature of A, which is 5,800. Yeah, 5,800. Sorry, I thought they were supposed to find the with respect to the sun, so it's not. So all the values have been given already. Sorry about that. Yeah. So yeah. Well, I mean, this is not MCQ, so um, I'm just gonna I'm just gonna screenshot this and send it out like that. And hopefully, whoever it is will know what I'm talking about. Yeah. Sorry about that. Okay. Let's move on. Yes, thank you. Um, this one I went through just now. So this one is the circular motion. Uh, the 5WR, right? So did I reply for this one? Did I send a reply for this one? If anything, I'll probably just yeah, I know you asked it, right? But then if someone's looking at it, like, what happens if the student needs it, right? Then you know what? I'm just gonna say, like, look for A2 because it's definitely inside the list, right? Look for A2 circular motion video. Okay, so this one's done. This one we also done already. This one here will be uh look for uh tandem 24th August video, right? So because we settled this. Oh dear, this one again. Okay, no, guys, specific energy is not in syllabus, so don't need to do this, please. Right? So specific energy not in syllabus. Oh gosh, I'm sorry if let's say it was my paper. Yeah. So just take note, right? Specific energy not in syllabus. And anyway, this was a pain in the ass question to do. There was a lot of controversy for this question the last time round for the previous batch. Yeah. How do we go about doing these questions again? You memorize stuff. Yeah, dude. All right. I don't know who this is, but yeah, you got to memorize this. So diameter of atom to diameter of nucleus. Oh, yeah, diameter of atom. So you gotta memorize this, man. All right. So yeah, what is the diameter of atom? That's the 10 to the power minus 10 meters. What's diameter of nucleus? Right, that's 10 to the power minus 15 meters. And then that's it, right? So 10 to the power minus 10 over 10 to the power minus 15. Yeah, that's pretty much it, right? So 10 to the power 5. Okay? So yeah, one more time. I repeat again. You have to memorize. Okay? For whoever it is, have to memorize. Okay, have to memorize here. Let me just Oh, the orange font is not the best, but okay. Then this one, thin film interference not in syllabus. I think I replied it, but yeah. All right, so I replied it. Yeah, thin film interference. Okay, but I swear, if your prelims come out right, I will crash out on the teacher. Seriously, damn freaking annoying. Okay, so this thing here, all right, I did say, okay. So honestly speaking, I think you don't have to care about the minimum thickness, right? Legit, you don't have to care about the minimum thickness. But there's this thing about these two light rays, okay? So let me just quickly explain this without going into thin film interference. Let me explain this in the context of like what you know, okay? So there's light falling on a thin film, like an oil film or soap bubble. This is actually a soap bubble, right? Yeah, the film, okay? Air, then soap bubble, then air, right? So the light is falling here and it hits the top surface of this film of water, okay? Right? And then it reflects off like that. Then a little bit more light goes in, right? Actually, quite a lot of the light will pass out, right? So what they didn't draw was actually the light that comes out here. So what happens here is that when light hits this point, it reflects a little bit as well, right? And then it comes out here like this. So then you have these two light rays coming out, okay? Right. Two light rays very near each other is pretty much like two source interference, okay? So depending on how much difference the path is, because if you look at the other one that went in and came out again, right? He traveled an extra path, right? So depending on how much the extra path is, right? These two light rays could be in phase or out of phase. And if it's in phase, constructive interference. If it's out of phase, it's destructive interference. Okay? Yeah. But other than from that, I don't think you need to know anymore, right? It's just essentially a different form of two source interference. Yeah, but it is our syllabus. Okay, so I'm just gonna move on to the next thing. Oh, someone dumped an album. Okay, this one here. Why is this question always coming out? Okay, this is in my A2, right? A2 lessons. I don't even know whether I should be doing this because majority of you should know how to do this, right? But I will do it very quickly. Okay? Please, please, please remember when you get this kind of questions, if this was your nightmare since secondary school, some of you, you just hated this since secondary school. I get that, okay? I get it. Why is the resolution so poor? I get that, right? If you're doing this kind of question, one more time again, please draw the forces acting on the objects individually, separately, right? Draw it for this guy, draw it for this guy, okay? So for mass M, there is a tension pulling it, right? There's a tension pulling it. And there's no other force acting on mass M. I mean, there's the weight and the normal contact force, but they both cancel. So T, T is the resultant force for M. T equals to big MA, okay? Which also means that mass M will accelerate off the table, towards the table like that. Now, a pulley is just a wheel. My other class, my JC class, some of them thought a pulley's job is to pull. No, it's not to pull. It's not something to pull. It's just a wheel that rotates. Okay, it's a wheel that rotates. Okay, I mean just in case lah. Right. Then you look at this one here, right? This W here, right? This W here, right? I'm gonna call him MG, right? Small mg, right? W is small mg. Okay, W is small mg because the other one is big M, right? So this one is small m lah. Okay. If you have this inclination thinking that, oh, tension and mg are the same, then there's something very wrong because this mass is connected to this mass via a string. If this mass is going to accelerate towards the right side, and if you tell me that mg is equals to t, that means it's going to hang here stationary, then something is wrong, right? That's not right, right? It can't work like that. You can't have something that's going this way and then yet this thing is attached and then not moving there, right? I mean, if it does, you know my like repeated joke how many times already, right? Just drop everything, go to the nearest temple and pray, because it shouldn't be happening. Okay, so you got to look at this mass and you got to do the calculations. You got to do the equations for this guy. All right, you have to recognize that small mg is actually bigger than the tension, right? Now the tension is not mg. The tension is m times a. It's gonna accelerate, but the acceleration is pretty small, I think. Right? So mg is actually bigger than tension. If t is bigger than mg, the mass will move upwards. That makes no sense. This mass will move downwards. So mg is more than t, and therefore we can write mg minus t equals to ma. So you're recognizing that this mass will also accelerate downwards at a. Again, another common mistake is some students think that, oh, it's falling, right? Why is it not falling at g? Because it's not free falling. If there wasn't a tension, it will free fall. Then the acceleration is g. But the acceleration is not g. It will accelerate, but it's not g. And the other thing is some students also, they get very confused by this. Oh, so is the acceleration of this and the acceleration of that, is it the same? Yes, it is exactly the same. Why? Because they're connected by a string. Whatever this acceleration is, the acceleration of this one must be the same. Okay? Then the next thing is the tension. Is the tension of this one and the tension of that one, is it the same? Yes, it's exactly the same because one string, one tension. Right? One string, one tension. So, you mean the acceleration at this one and this one is the same? The tension of this one and this one is the same? Yes, it is. It's the same magnitude, right? Pointing different directions. This one pointing towards the right. This one pointing downwards, right? This one, the tension pointing towards the right. This one, the tension pointing upwards, right? You're just drawing the forces for the individual objects. And I swear to you, you work it out, it's gonna work out, right? So what you need to do now is you have two equations. You got this one here and you got this one here, right? You basically need to manipulate this and this so that you can get one of these, right? Yeah, one of these. Okay. So it looks like there's a W, right? It looks like there's a W. They don't use small mg, so I'm gonna swap this out for like W. Okay, right? W here. They don't use small m. I just substituted it myself, small m. So technically speaking, you kind of like have to show small m, right? So I'm going to replace this small ma with w, but divided by g. Because w divided by g will be small m. And then put an a here like this. Now, okay. So now I have to decide what to swap in and all. So basically, I'm going to sub this into that one there. So w minus ma equals to w over ga, right? And then w equals to w over g plus m bracket a. Because I move it over the other side and I factorize the a, so w over g plus m. Then therefore a is equals to w over g plus m. And thankfully I don't have to thankfully I don't have to um like manipulate anymore because I'm like there's a lot of letters for me already. That's the answer here. Okay, so there you go. That will be for this. Okay. Wait, sorry guys, what? Yeah, I'm having consult. Hang on to 1 minute. Let me just finish one message because I need to arrange for. Okay. Hang on. There we go. Okay. Sorry for that little bit there. So this one here, it's yeah, so no pivot, right? So this one here is just the mass, right? The particle will hit the mass, right? Sorry, the particle will hit the rod like this. No pivot means that the whole thing, right, will accelerate downwards. Like they'll move together. Yeah. So it'll be like a normal collision type of situation, right? Conservation of linear momentum. Yeah. So whoever's asking this, but I think um yeah, it will move along a straight line. So yeah, it will rotate about its center of mass. So yeah, I think this one here I'll explain post prelims. Yeah. So you know what? Actually, I'll just leave this in unfinished business. Oh, actually, I finished this business already, so I'm gonna delete this one. Right, so I have unfinished business here. Don't you just like Telegram? So much better than that. Okay, this one here. um, can anyone tell me where this is from? Sorry. Does anyone know where this one is from? I see a lot of markings, so I kind of like want to try to get rid of it. I want a cleaner copy of it. No? I mean, I've done this many times over the years, but I just don't remember what in particular. So it's actually, since I've done it so many times, I actually just incorporate it into my notes, right? It's like then I don't. Sorry. Okay. So the topical MCQ. Okay. Thank you. Um, topical A2. Okay. See, right, A2 is kind of scary, isn't it? Yeah, it happens. The easy topics, they will come up with very difficult questions, and the hard topics, they will come up with easy questions. So those who try to be funny, you will end up burning yourself. This one? And oh gosh, which number? 14. Yeah, this one here. Okay, cool. Let me just screenshot this one. Okay. So we have so this person is pushing this mass, right? This M here is rolling freely along the road, so there's no friction at the bottom, it's smooth. Okay, right? So you're pushing it. So they're asking you what's the maximum acceleration of the table. This is the table, so that the book doesn't slide backwards. So for the book to slide backwards, basically there's not enough static friction. Do you understand that? The sliding part, the sliding backwards part. Sorry, Jillian. Oh, okay. Sorry. Okay, so sliding backwards means that the book receive enough, doesn't have enough static friction, right? So kind of like if there's not enough static friction, the book will slide backwards. So the idea here is the maximum acceleration of the table so that the book doesn't slide backwards means that the book is experiencing the maximum possible static friction, right? Because if you don't want it to slide backwards, that means it's got to remain like in position with the table, right? Therefore, the book will experience a static friction this way, right? This is mu Sn, and it's static friction. It's not even dynamic friction because the whole idea is that the book um remains at rest relative to the table, right? So remains at rest relative to table, right? So this kind of shows you that this is a static friction, right? Therefore, static friction, right? Yeah, I tell you, a lot of people will complain about this. Like, what? Why am I supposed to? I thought the table and the book is moving. Yes, the table is moving. The book is also moving together with the table. But because it's moving, right, together with the table, the static friction keeps the book from sliding backwards on the table, right? So this is static friction. It is not dynamic friction. Okay. Anyway, they don't even bother, right? They didn't even care. They just say coefficient of friction, right? But I do things properly, right? So it is static friction, right? So static friction, right, prevents the book from sliding backwards. Okay. Um. So kind of like what's the maximum acceleration of the table? Okay. So this person is pushing it along. I don't even see a force acting on it. Okay. I mean, so that means that this is the max F net, right, on book, right? That's the maximum net force on book because there's no other force acting on it, right? So you have mu s n equals to small ma, right? Um, and if you ask me for maximum acceleration, then it's just simply a equals to mu s n static friction coefficient times normal contact force divided by small mass, right? But lo and behold, we don't have n, right? So the normal contact force. So we need to figure out what's the normal contact force. So the normal contact force here, but that's just equals to small mg, right? So maybe we can just substitute in and see whether we can get it. So substitute n with mg and therefore divide by m, right? And that's all is mu sg. Wow. Okay. Yeah. So the acceleration works out to be this. So just B's answer. Okay? Right? But yeah, it's gonna be a very uncomfortable question. There we go. Okay. This one here. Did I not do this? Guys, did I not do this? I thought I did this. Hmm. Yeah, I can't remember. But anyway, okay, fine. I'll do it. So direction of the magnetic field is quite right, right? Right hand grip rule. Right. Sorry, right hand grip rule. This is my right hand. Yeah, to your mirror image, that's my right hand. So right hand grip rule, that's correct. Okay. Yeah, so going in and then turning that way, that's correct. Right hand grip rule is correct. So why don't you just commit? Like draw it at point Q, like draw it where Q is, like just commit lah. Yeah. So this is the magnetic field of P here, right? And then this would be the magnetic field of R, right, pointing upwards like this. Okay, right. So this is like B of R, right? Yeah. So at point Q like this, so you got one going towards the left. Yeah, you're right. You're right. I mean, commit lah. I mean, whoever doing this, please just commit. Just draw a bigger circle, right? Draw it there. Draw it at Q. They're asking for at Q, right? They ask you, um, the magnetic field due to P at Q is X. So that's X. This is X now, right? I mean, I wrote BP, but it's X, right? Same current. So you know what? This also gonna be X as well, right? Then they ask you what's the magnitude of the resultant magnetic field? Oh, resultant is just you got one X this way, right? You got yeah. I think you can get this already, right? You got one X this way, you got one X this way, right? You're basically trying to find the resultant, which is like the Pythagoras, right? So it's gonna be C lah, right? Yeah, vector sum. Magnetic field is a vector. Yes, it is, right? You thought vectors are supposed to be straight arrows. Yes, you're right. Okay, magnetic field is a curved line, but when you take a magnetic field at a point, it's a tangent to the curve. So magnetic field is a vector sum. right? So you Pythagoras this thing, right? Pythagoras, right? Pythagoras, right? Vector sum, right? So yeah, there we go. And then we have this one here. Okay. Um. Oh boy. Oh, this is gonna be a doozy, right? You guys are gonna love this one. No, actually, you would probably hate it. So, charge flows through a liquid. Charge flow is made up of positive and negative ions. In 1 second, 0.1 C of negative ions flow in one direction and 0.1 C of positive ions flows in opposite direction. I'm gonna draw this out. I'm gonna visualize this for you, right? So you have a liquid, right? Right. In that 1 second, right? In the 1 second, you got negative charges, negative charges flowing in one direction, right? And then you got positive charges, positive charges flowing in the other direction, like that. Yeah. And there's 0.1 C of the negative charges, and there's 0.1 C, by the way, is 0.1 coulombs, in case I don't know. I need to be explicit, right? Okay, right? So you know what's the thing that tricks students on this? They think that, hey, one flows this way, the other flows this way, then the total current is zero lah, right? Absolutely wrong, dudes. Right? Don't forget, negative charges moving to the right, current is pointing to the left. Positive charges pointing to the left, current is to the left, right? The current here is created by both, right? The negative and positive charges flowing in opposite directions. So current here, yeah, the current is the combined of the flow of the two charges, right? So the I is equals to 0.1 over 1 second plus 0.1 over 1 second, right? So 0.2 amperes. Okay, so this is the answer. Don't get tricked, right? I mean, many years already this question, right? So the current is pointing backwards for the negative charge, and the current is pointing forwards for the positive charge. Okay, so I'm just gonna screenshot this one and send it to you. Okay, sorry, the mug. This one here. Ooh. So rope breaks when angular velocity omega is reached. What other combination? Okay, all right then. We'll see how to do this then. Okay. So do you realize one thing that I'm doing this? Like I want to repeat myself again. It's my job, right? If I were to sit in for an exam and I get a question like this, I will always draw it out. Like I legit will draw it out myself. Like even though you tell me that, oh, you got so many years of experience, you don't need to do this kind of things. No, dude, I will draw it out. Right? The years of experience tells me that I have to draw it out. I should draw it out. I don't trust my brain. I trust what I see. You know? Yeah. Because my brain sometimes is like, oh, it skips a beat sometimes. You know? So yeah, draw it out. Then you don't have to juggle so many mental things. Right? Draw it out, draw it out. Okay? Most of the time you realize that, oh, I realized that I didn't draw it out, that's why I got it wrong. You got a horizontal circle. Not bad. Okay. Mass M attached to a rod, rotated in a horizontal. So it's a horizontal circle. So this is the top view, right? So there's nothing to do with like vertical circle. It's not like losing GP or anything like that. It says that it's the speed is increasing and the rope breaks when angular omega is reached. So you know what? Let's just draw the forces acting on this mass, right? That's the tension, right? So it's like tension. So the rope breaks when it reaches omega. So you know what? I'm gonna assume that that's T max, right? Because that's the maximum force that will cause the rope to break, right? So T max is equals to mr omega squared. Right, r omega squared. So once I reach omega, that will give me T max, and therefore the rope will break then. Okay. So the question is, which other combination will give me the same T max as this? Like I mean, I can see some of them is mass is divided or whatever it is, right? Multiply is the mass is multiplied and then the omega is divided. So which other combination will give me the same T max, right? Will the rope break? Okay. I mean, all I have to do is just try to fit it in now, right? So I'm looking at it. Looks like D's answer. Looks like it. So let's try this one. This is like T2, right? Okay, the second one. That will be like 4m times r. They didn't change r, right? They're still using the same rope. And then times omega squared, right? Omega over 2 squared. So don't forget to square it, right? So square it like this. So this turns out to be mr omega squared. So it's the same one, right? Yeah. Okay. So yeah, that's the answer. Okay. Um, I'm just trying to see whether there's any other combination that will give me even more. But you know what? If you can get the same answer, it's correct already. Okay, there we go. Oh, you're not gonna like this one. Jeez. Yeah, I guess in a way it's great, right? Because like, that's my job, right? Tackle the challenging questions. Okay, you're not gonna like this one. Okay. Read very carefully, P and Q are two opposite point charges, right? Which means that one of them is positive, one of them is negative. We don't know which one yet. Right? Force acting on P due to Q is this force arrow here. That makes sense because they are oppositely charged. They're supposed to be attracting each other. So that would make perfect sense, right? So this force is force on P by Q, right? And it's an electrostatic attractive force. They're attracted plus attracts minus. Okay? Okay. But you see, the E field strength at P is shown. Okay, so the big question is, whose E field strength is this? Okay, all right. They didn't say that the E field strength of P is shown. They show you the E field strength at P. So so you literally will have to take it as this, that right, P is not the one that created this E field strength. This E field strength is by Q acting on P's position. So this E is by Q at P, right? I mean, it's hard to accept, but that's why this question is a little bit more like I've done this question many times over the last 2 to 3 years, right? Because of this, right? Like a lot of students don't realize that, oh, but I thought the P is positively charged because isn't the E pointing out of P? But it's not because they say this is an E field at P due to Q, right? So in a way, right, Q is a positive charge, and positive charges have field lines pointing outwards like this. P just happens to be a negative charge that's sitting here, right, in the path of Q's E field, right? And that is why P experiences a force pointing that way, right? So the force, oh, that's a bad color, right? The force acting on P is pointing this way. That's why the force is like that. Okay? That's the context of what that first sentence means. Then now they're gonna ask you, what is the force on Q due to P and what's the E field strength at Q? That means at position Q. So it's the other way around, right? You got P here, negative charge, right? And then the kind of like it's a negative charge, right? So what is the E field strength of P, right? Where is it pointing? Negative charges, the E field strength points inwards towards the negative charge, like this, right? And then you see, right, that's the thing. Q happens to be sitting there, right? So Q happens to be sitting on his line, right? So this is Q, like that, right? And Q is positively charged. So number one, right? Q experiences an attractive force, so definitely force will be pointing this way, right? Force is pointing that way. And the E field strength of P at position Q is also pointing towards the left, right? And therefore this answer here is like that. Like this is E by P on Q. No, not on Q, sorry, at Q. At Q. Okay? So this one, like the answer would just be B lah, right? Because they have to be pointing both in the same direction towards the left side. Right, so whoever's asking this, right, I think I'm gonna screenshot this, but unfortunately I think, you know, if without explanation, this thing is not easy to be seen on the on the screenshot. So I will just inform whoever it is, right? Please refer to ACSi prelim consult done 24th August 2025 tonight, the 9:30 p.m. one. Oh shoots, it's 1 hour plus already. It's okay. I mean for me, but I will try to wrap it up. This is on Heisenberg's uncertainty principle. This is not in syllabus, right? I'm so sorry if it appears in my worksheets and you're thinking that it appears. And then let's do this one, right? Fireworks. Okay, fireworks. There we go. Right, so question of fireworks here. So it says launch vertically, explodes into two pieces. Mass of X is greater than Y. They ask you which of the statements is correct. Okay, right? So we have to, yeah. So we have a firework that's being launched upwards like this, right? So it goes up, phew, and then it breaks into two parts. So I'm just gonna draw like, you know, one fragment and another fragment, a little bit smaller. Yeah, okay, something like that. All right, so it breaks into two parts. Okay. Mass of X is greater than Y. Okay. So three statements about the pieces immediately after explosion. They ask you, Ke of X is less than Y. Magnitude of momentum is equal to that of Y. Total momentum after the explosion has increased. Okay. Number one, I would definitely disregard statement 3. Okay. Right. Total momentum after the explosion should not have increased because the momentum should be conserved. So what happens is that the momentum of this firework, right, the initial momentum, right, the total momentum should also still be, right, the final momentum of the two fragments should still be equal to the initial momentum, which is basically the m times the velocity upwards. Yeah. So you should be able to infer that if you did have two fragments exploding like this and they kind of like exploded and they went separate ways, you would expect them to go this way and this way, like that. Okay. Yeah. Yeah, both ways. Okay. Then you will this will be like the momentum of X and this will be the momentum of Y, right? The leftwards momentum of X will balance the rightwards momentum of Y. The both vertical momentums of X and Y should add up to the initial momentum of PI. Okay. So for the answer for this one here is definitely just A. You can walk away with this because once you know statement 3 is wrong, there's no other options. You walk away with you know, just A is the answer. Okay. You if you want to go and show kinetic energy is less than that of Y and the magnitude of momentum is equals to that of Y, right? We can um we can show that, right? But it's not worth it at this time. Yeah. Okay, because this is just a by elimination 3 is wrong, so you know, yeah, it can't be right. I'm chasing up. I'm almost done. Oh no, actually no. I still got a lot. Okay, hang on. Let me just try to speed things up a bit. Oh boy. Okay. So the key word in this question here, please take note that they say stationary halfway, right? Straight away you need to recognize that it means that the particle's weight has to be considered. So which means that your particle, right, you need to consider weight. If the particle has no weight, if you come and say like, oh, but I thought you said that last time, right? Charged particles don't have weight, right? Or the weight is negligible, right? You're misinterpreting what I'm saying, right? I'm saying that, right? Oil droplets, you definitely have to consider weight. Charged particles, you need to check, right? Since it says stationary, we have to infer that the weight balances the electric force, right? So you cannot like, you know, just simply just quote like misquote what I said and then say that, oh, I thought I said weight is negligible. Okay, right. So oil droplets, you need to consider weight. Charged particle, you need to check. Right, so the electric force is there. So what's the magnitude of the electric field and the direction of the electric field, right, at the position of the particle. So it turns out this particle is negatively charged, right, negatively charged. So we'll put a negative sign on it, right, it's negatively charged, okay, negatively charged. And it experiences a force upwards, right? Here's the trick, right? If your negative charge experiences a force upwards, the field is pointing the other way, right? So the field is definitely pointing downwards. Okay, the field must be pointing downwards. The E field must be pointing downwards. I'll show it to you later, but it's negatively charged, right? Well, in a way, in order for a negatively charged object to be suspended, for the electric force to be pointing upwards, the top plate must be positive, right? The bottom plate must be negative, right? So the E field line, if you were to draw the E field line go from the plus plate to the minus plate, right? Like so, right? From plus plate to minus plate like this, right? So the E field is pointing down. So, direction of E field is pointing down. Okay, now we have to figure out what's the magnitude of the E field, right? So it says that V between them and distance of D separation is just straightforward. There's no other option, so it has to be D. Okay, right? So yeah, I think for whoever was trying this question, right? I think the confusion was, do I choose it upwards or pointing downwards, right? You got my answer. Okay, so you have to consider weight. You know that electric force pointing up. Negatively charged object. If electric force is pointing up, the E field is pointing down. Okay, because the E field is meant to be defined for the positive charge only, right? A positive test charge. Okay, there we go. Right, so yay. Okay, then we have this one here. Sorry. Okay, this is not in syllabus. This has something to do with Schrodinger's tunneling, right? So it's something to do with tunneling. I think I reached the end, right? So this is not in syllabus. In syllabus, Schrodinger tunneling, right? If you are interested to read up more, that's why I write the name down. Schrodinger's tunneling. It's actually a very interesting concept. Okay, uh, tunneling. It basically, right? I hate to say it, but it basically shows you that particles can. Okay, I'm not going to use the word teleport, but the idea is it can teleport across boundaries. Okay, particles can, and this is not science fiction, right? In your seniors batch, the previous syllabus, I had to teach them, right, that particles can teleport across boundaries. Okay, right? But yeah, then we have this one here. Oh gosh, what's this? Almost done, almost done, almost done. Catching up, catching up, catching up. What's the acceleration of x versus the acceleration of y? Um, if you move across a certain distance L, right? If you move across the certain distance L, the big wheel will have to turn yeah. The big wheel have to turn 2 pi 3r. Oh gosh, I'm so bad at this. And then the small wheel will have to turn, I mean circumference is 2 pi r. So for the same L, y must turn 3 times more. No, yeah, 3 times more. Right? So for every one rotation of x, right? This is equals to 3 times rotation of y. Not yet. Yeah. I I I I want to, but they have exams. Okay, well I'm stuck with this one. Okay, acceleration. Firstly, acceleration. Why is it acceleration accelerating when there's constant speed, right? Shit. This is centripetal acceleration. Centripetal acceleration. This AC. This is R omega squared. So AC of x over AC of y. This is x is 3r times omega. Omega is 2 pi over t. One rotation of x. Then y is r. So every time x does one rotation, y has to do 3 rotations. So 3 times of 2 pi over t squared. Something like that. I know. My wife says that the kids needs to sleep. Really? Do you guys need to sleep? So it's 3 over 9. 1/3. I think this answer. I think this answer. I'm eyeballing it. So 3 on top, 2 pi over t squared is the same as the bottom 2 pi over t squared. The only difference is there's a 3 squared, so it's 9, so 3 over 9. That's I'm eyeballing it like this. So I believe this answer. I'm so sorry if I got the wrong answer, but I think this should be the answer, right? Because here's the thing, I'm getting very confused by this, right? It's constant speed, but then asking me for acceleration. So the only thing I can think of is centripetal acceleration. It cannot be angular acceleration. This is not A5. This is a A2 question. But it's such a strange question. I don't know where this is from. Sorry. I've been talking a lot. Oh. So I think I see some semblance of this, but doesn't seem like you understand what's going on here, right? This is this is um this is in my E2 or E3 videos somewhere there. I'm very confused. I also can't remember. This is the estimating the nuclear size. This is the most accurate method of estimating the nuclear size, right? By using electron diffraction. So theta, well actually it's not a small angle, so sine theta minimum equals to lambda over d. This is because this is small. Um this is obstacle diffraction. Obstacle diffraction. So I won't go through this now. So I'll just point out that this is under the one of the E videos, right? But yeah, if you do have double the diameter, but you have the same speed, means that you have the same lambda, right? So same electrons of the same speed will give you the same lambda because we're using the electrons as a wave now. So this is the electron wave duality, right? The particle wave particle duality. So we're using the same speed, so same lambda. So with the same lambda, then they ask you like, but directed at nuclear y has double the diameter, so it's 2 times the size, right? So what will happen to, right, the angle sine theta minimum of y equals to lambda over 2d, right? So sine theta minimum of y will be like, half of that. So, but they didn't ask for that, so theta minimum will be like decreased, right? So it will decrease. Okay, so it's decreased, right? And then the nuclear density is the same. It's exactly the same, right? Nuclear density. So whoever is asking this question, right? You are missing the idea of what nuclear density is, and you're also missing the idea of what nuclear size is. So basically, this whole thing seems to be lost on you. But I do see a semblance of what you're trying to do here, but it just doesn't seem like you understand fully. So the best thing is, and furthermore, didn't this happen in the ACSi CTs? Right? I think this was the case, right? So if you're still unsure about this and you're still unsure about that, all I can tell you is that you have to watch the video because that will take too long. This is going to take me too long to go through the whole concept, right? So please do not hope that I can squeeze in everything in 5 minutes. That's not feasible, right? So please refer to e-videos for number one, nuclear density is the same for all nuclei. Number two, estimating nuclear size, right? The third method, right? The most accurate method, right? Which is basically the electron diffraction method. Electron diffraction, right? With nucleus as obstacle. Okay, so it's definitely in there, but you have to go through. You have to really bite the bullet and go through the whole thing. Um, did I not go through this? Yeah, I think I went through this afternoon. Whoever's asking for this, right? This one here, I kind of like did this. So we have 5 volts here. We have 5 volts here. This is sorry, right? The other one is 5 volts here. This is 2 ohms and this 2 ohms. Batteries in parallel, it becomes one single 5-volt battery, right? The voltage doesn't add up, but resistors in parallel, you add it up in parallel, it becomes 1 ohm. Then you just solve it like this. Okay, so batteries in parallel, same voltage. Resistance in parallel, parallel resistance, right? So then you solve it. I'm not gonna show the working for this. I think this should suffice for whoever is asking this. I don't know who it is. All right, there we go. Okay, so that will be for that one, and then we have this one. The last one here is this. Sorry, who's asking this one? Is that the last one for tonight? Shit. Yeah, that's the last one plus this one here, right? So this is not in syllabus, right? Whoever this asking, right? Not in syllabus. Schrodinger's tunneling. Okay, good. Right, we end off with that one. Oh wow, what a way to end. This is bad. Gee whiz. Oh, this is bad. This is so bad. This is horrible. Um, what's the tension when the string is horizontal? Like, what's the tension here? So the thing that really irks me is the fact that they say it's a vertical circle. Uh, I am just gonna say that I'm just gonna take a gamble and just say that tension equals to mv squared over r. Zero. Hey, sorry, who's the one who asked this? Are you in the group now? Who's this? Sorry? Oh, okay. Is the answer not this one, mv squared over r? I think it might not be. But otherwise, I, I don't see any other way to do this question. So it's like 0.3, 0.6, half of 4 squared, half of 16. So is the answer B? Yes, a stupid question, right? This question is very annoying. Okay, sorry. Yeah, I thought it was bad at first, but this whoever is setting this question is an annoyance lah, right? Like they try to be funny here, and then they talk about vertical circle. Yeah, no, not a good question at all. Not yeah, as in not the person who's asking. Like, it's like this person who said whoever said this thing, right? He's trying to be like tricky and then talk about like what vertical circle, and ask you what's the tension when the string is horizontal and all that. No, so it's got nothing, right? So it's just plain old like tension is equal to mv squared over r, and then that's it. Yeah. Okay. Yeah, that's all there is to this one here. All right. I'm gonna call it a night. It's really quite late, and I don't think I have enough. Oh, sorry. Is there more questions coming in? Oh no, that was me, right? Okay. Did I have do I have any unfinished questions for you guys? With you guys? Anyone? Unfinished MCQ questions? No? If not, then oh, sorry, did anybody chat here? Oh no, no one chat here. Okay, if not, then I'm gonna call it a night, right? All the best for tomorrow. I'll see you guys on Tuesday, right? Yeah, I'll see you guys on Tuesday because we are going to go through um the paper twos. Is there any SLs on board? Any SL here? No. Oh, Keegan. Hello, Keegan. Hey, so I'm gonna hold a separate SL consult for paper two on Tuesday. Hello? Yeah, so I think I'll probably see you guys before I see the rest of them. So I'll probably see you guys at, I don't know, is 1 o'clock a comfortable time? Yeah, 1 o'clock. Yeah, because I heard that there was only Langlit on Tuesday. Yeah. I mean, yeah, you check with them if they want to be if they want to be online and all that is okay. But I just feel like I should separate the SLHL because the HL might end up having a lot of HL questions to ask, right? Then if you want to, you can sit in continuingly sit in for the HL side and then see if you've got any questions that you want to ask. Okay, right? So tentatively it's 1 o'clock, but if you want a bit earlier, I also can do that. Maybe 12:30 to if you want to be comfortable. Can? Right, see you, man. Thanks. Bye. Cassandra, Mansa, do you have more questions to ask? No? Okay. Yes, Mansa? Oh, okay. Thanks, Mansa. Thank you. You're welcome.